When we speak of time, we must first understand that time is not what we think it is. Um, it is not this absolute thing flowing like a river, independent of everything else. No, no, time is, how shall I say, time is woven into the very fabric of reality itself, you see. And this realization, this understanding, it changed everything, everything. Let me take you back to a moment of deep contemplation. Imagine yourself sitting in a patent office. Yes, a patent office in Bern, examining applications for new inventions day after day. The mind wanders, doesn't it? The mind asks questions. And one day a simple question arises. What would happen if I could ride alongside a beam of light? What would I see? Would time stop? Would the light appear frozen in space? These questions, simple questions really, they open doors. Doors to understanding that had been closed for centuries, you understand. Because you see, we had been thinking about motion all wrong. We thought that if you measure something moving at a certain speed and you yourself are moving, you simply add the speeds together. Common sense, yes? But nature has no obligation to match our common sense. Consider this, if you will. You are standing on a train platform, and a train rushes past you at great speed. On top of that train, someone throws a ball forward. How fast is the ball moving from your perspective on the platform? You add the speeds naturally. Simple arithmetic, the way we have always understood motion. But now imagine that train is moving at nearly the speed of light, and instead of throwing a ball, someone shines a flashlight forward. How fast does the light travel from your perspective? The speed of light plus the speed of the train? No, no. This is where everything becomes strange, you see. The light travels at exactly the same speed as it would if the train was standing still. Always the same speed, always. This is not intuition. This is observation, measurement, reality telling us something profound about itself. The speed of light in empty space is constant, constant for everyone, regardless of how they are moving. This simple fact, this one constraint that nature imposes, it forces everything else to change. Time must change. Space must change. You see, if the speed of light is the same for everyone, then two people moving relative to each other cannot agree on when events happen, or even on how long things are. Time itself becomes flexible, malleable. It stretches and compresses depending on motion. This is what we call time dilation, yes? A moving clock ticks more slowly than a stationary one. Not because there is something wrong with the clock, but because time itself, the very passage of time, runs at different rates depending on motion. And this is not philosophy. This is measurable, testable reality. We have taken atomic clocks, the most precise timekeepers humanity has ever built, and flown them on airplanes. When they return and we compare them to identical clocks that remained on the ground, the traveling clocks have measured less time. Less time has passed for them. The difference is tiny, incredibly tiny, because airplanes are so slow compared to light. But it is there. It is real. Now imagine if you could travel much faster, close to the speed of light itself. If you were to board a spacecraft traveling at extraordinary velocity and journey to a nearby star and return, you might experience only a few years passing. But when you return to Earth, decades might have elapsed. Your twin brother, if you had one, would be an old man while you remain young. This is not science fiction, though it sounds like it. This is what the mathematics tells us, what the structure of space-time demands. Space-time, yes, we must speak of space-time now. Before these insights, we thought of space as a three-dimensional stage where events unfold and time as a separate universal clock ticking in the background. But they are not separate. They are unified into a four-dimensional structure we call space-time. An event is not just a position in space, but a position in both space and time together. And motion through space is intimately connected with motion through time. Here is something beautiful, something I find truly beautiful. Imagine space-time as a fabric, like a stretched sheet. When nothing is there, it is flat, smooth. But when you place something with mass on it, the fabric curves. It dimples and warps around the mass. The more massive the object, the deeper the curvature. And now other objects moving near this curvature, they do not feel a force pulling them. No, they simply follow the natural paths, the straightest possible paths through this curved space-time. What we call gravity, what Newton described as a mysterious force acting at a distance, is actually just objects following the geometry of space-time itself. The Earth orbits the Sun not because a force pulls it, but because the Sun curves space-time around it, and the Earth is simply moving along the curved path that geometry creates. This idea, this geometric understanding of gravity, it came from years of struggle, of trying to reconcile gravity with these insights about time and space. You see, the earlier understanding, what we now call special relativity, it worked beautifully for objects moving at constant speeds. But gravity involves acceleration, changes in motion. And to understand gravity, we needed to expand these ideas, to generalize them. Thus, general relativity was born. The mathematics, oh, the mathematics is complex, I will not pretend otherwise. Tensor calculus, differential geometry, equations that describe how matter and energy curve space-time and how that curvature tells matter and energy how to move. But the concept, the physical picture, it is elegant. Matter tells space-time how to curve, and space-time tells matter how to move. A perfect feedback loop, a dance between geometry and substance. And from this understanding came predictions, strange predictions that seemed almost impossible. One prediction was that light itself should be affected by gravity, not because light has mass in the traditional sense, but because light travels through space-time. And if space-time is curved, light must follow that curvature. So a beam of light passing near a massive object like the sun should bend, should deflect from a straight path. During a total solar eclipse, astronomers led by Arthur Eddington observed stars near the sun in the sky. The sun's glare usually makes this impossible, but during the eclipse, the stars became visible, and they appeared shifted from their normal positions exactly as predicted. The light from those distant stars had been bent by the sun's gravitational field as it passed nearby. This observation, this confirmation, it made headlines around the world. Suddenly, these abstract ideas became real in the public consciousness. But there were other predictions, stranger ones, black holes, for instance. If you compress enough mass into a small enough region, the curvature of space-time becomes so extreme that nothing, not even light, can escape from within a certain boundary. We call this boundary the event horizon, yes? Beyond this point, all paths through space-time lead inward. There is no outward direction anymore, in a sense. Time and space exchange roles in this region. It becomes difficult to even describe in words. For many years, these were considered mathematical curiosities, perhaps not real objects in nature. But now, we know better. We have observed the effects of black holes, seen stars orbiting around invisible massive objects at the centers of galaxies, including our own Milky Way. We have detected gravitational waves, ripples in space-time itself produced when black holes collide and merge. Facilities with remarkable precision have captured these waves, disturbances in space-time smaller than an atomic nucleus traveling across the universe to reach us. The Event Horizon Telescope collaboration produced an actual image, an image of the shadow of a supermassive black hole in a distant galaxy. The theory predicted what we should see, and there it was, real, tangible, visible. a dark circle surrounded by glowing matter, forever falling inward, forever trapped by geometry itself. Gravitational waves. Let me speak about these for a moment. According to general relativity, when massive objects accelerate, they should create disturbances in space-time that propagate outward at the speed of light, like ripples on a pond when you throw a stone. But these ripples are incredibly weak by the time they reach Earth. The most violent cosmic events produce distortions here that are astonishingly small. For decades, many thought we could never detect something so tiny. But human ingenuity is remarkable. The first detection came from two black holes spiraling into each other, merging billions of light years away. The waves from that event traveling through the vastness of space for over 1 billion years finally reached our detectors here on Earth, and we measured them. We felt the universe itself trembling, speaking to us across unimaginable distances. This opened a new window, you see, a completely new way of observing the cosmos. Light has been our messenger for all of human history, our only way of seeing beyond our world. But gravitational waves carry different information. They show us events that produce no light at all. They penetrate regions where light cannot escape. We are now listening to the universe as well as looking at it. And what stories it tells, what stories. Colliding neutron stars that forge heavy elements like gold and platinum in their death throes. Black holes that dance around each other for millions of years before finally merging. The universe has a voice, and we have finally learned to hear it. Now, let us return to something perhaps even more fundamental, more intimate to our daily experience. Energy and mass. These two are not separate things, as we once believed. There is an equivalence between them, a deep connection expressed in what has become perhaps the most famous equation in all of physics, E equals mc squared. What does this mean, really? It means that mass is a form of energy, concentrated, condensed energy. The c squared part, the speed of light multiplied by itself, is an enormous number. So even a tiny amount of mass corresponds to a tremendous amount of energy. A single small stone, if it could be completely converted to energy, would release enough power to light entire cities for weeks. Of course, in everyday processes, we do not convert mass entirely to energy. Chemical reactions, burning wood or gasoline, they rearrange atoms and release energy, but the mass change is negligible, unmeasurable with ordinary instruments. But in nuclear processes, in the sun's core where hydrogen fuses into helium, or in nuclear reactors here on Earth, measurable amounts of mass are converted to energy. The products of the reaction have slightly less mass than the ingredients, and that missing mass has become energy, radiation, heat, light. The sun, our sun, it loses millions of tons of mass every second through this process. Millions of tons converted to the light and heat that warm our planet, that make life possible. And it can sustain this for billions of years because it is so massive to begin with. This is the power of that simple equation, operating on a cosmic scale, painting the sky every morning. Before we continue, I would like to ask you to subscribe to the channel to help me reach the first 1,000 subscribers here. The purpose of this channel is to help you fall asleep with high-quality knowledge, right? It doesn't cost anything. Just hit that subscribe button. Now, this understanding also tells us something about the nature of matter itself. What is mass? Why do particles have the mass they do? For a long time, this was simply taken as a given, a property particles just have. But we have developed theories about how particles acquire mass through their interactions with fields that permeate all of space, what we call the Higgs field. Experiments at the Large Hadron Collider confirmed the existence of the Higgs boson, the quantum associated with this field. Another prediction, another confirmation that our mathematical descriptions of nature, strange as they may seem, correspond to reality. But let us think about light itself a bit more deeply. Light is electromagnetic radiation, yes, an oscillation of electric and magnetic fields propagating through space. Before the insights we have been discussing, there was a puzzle about light and electromagnetism. The equations describing electromagnetic phenomena, Maxwell's equations, they predicted that light should travel at a certain speed. But speed relative to what? Relative to what reference frame? If you believe in absolute space, a fixed background against which all motion occurs, then perhaps light travels at this speed relative to that absolute space. But then someone moving through that space should measure light at different speeds depending on their direction of motion, just as someone on a train measures thrown balls at different speeds. Yet experiments, careful experiments by Michelson and Morley and others, found no such variation. Light always traveled at the same speed regardless of the motion of the source or the observer. This was deeply puzzling, deeply troubling to physicists of that time. They proposed all sorts of explanations, you see. Perhaps there is an invisible medium called the ether through which light waves propagate, and perhaps objects contract as they move through this ether in just the right way to hide the motion. But these explanations, they were adding complexity, inventing invisible mechanisms to preserve old ideas. The actual answer was simpler and more radical. There is no ether. There is no absolute space. The speed of light is a fundamental constant of nature, and it is space and time themselves that must be relative, must adjust to preserve this constancy. Electromagnetism, as described by Maxwell, was actually already consistent with these ideas. We just had not realized it yet. The theory of relativity showed that Maxwell's equations are, in fact, more fundamental than Newton's laws of motion. Newton's laws needed to be modified, but Maxwell's equations remained valid. There is something profound here about the unity of physics. Different phenomena, seemingly unrelated, turn out to be connected at a deeper level. Electricity and magnetism, once thought to be separate forces, were unified into electromagnetism by Maxwell. Then we found that space and time, separate concepts for all of human history, are unified into space-time. And later, much later, physicists discovered that electromagnetism and the weak nuclear force, the force responsible for certain types of radioactive decay, are actually different aspects of a single electroweak interaction. This search for unity, for simplicity beneath complexity, it drives much of theoretical physics. Nature, at its deepest level, seems to operate according to principles that are beautiful, symmetric, interconnected. Why this should be so, I cannot say. But it is a source of wonder, endless wonder. Perhaps the universe, in some sense we do not yet understand, must be comprehensible. Perhaps consciousness and cosmos are linked in ways we are only beginning to glimpse. Let me tell you about another consequence of these ideas, something called the relativity of simultaneity. This is perhaps one of the most difficult concepts to grasp because it contradicts our everyday experience so completely. We think of now as something absolute, something universal. If two events happen at the same moment, they happen at the same moment for everyone. Yes, but this is not true. This is not how the universe works. Imagine two lightning bolts strike at different locations. You are standing exactly midway between them, and you see the flashes at the same instant. You conclude, reasonably, that the lightning strikes happened simultaneously. But now imagine someone else is moving rapidly toward one strike and away from the other. The light from the strike they are moving toward reaches them sooner, before the light from the other strike. They will conclude that the strikes did not happen simultaneously, that one happened before the other. Who is correct? Both are. There is no absolute simultaneity. Events that are simultaneous in one reference frame are not simultaneous in another. The very concept of now at distant locations is relative, dependent on motion. The present moment is not a universal slice through time, but something that depends on the observer. This has profound implications. It means the future, in some sense, already exists. The past still exists. All moments in time have equal reality. They are all part of the four-dimensional structure of space-time. We experience time as flowing, as a succession of present moments, but this may be an illusion, a consequence of consciousness, not a fundamental feature of reality. The universe viewed from outside time, if such a thing were possible, is a crystallized whole, unchanging, eternal. Does this mean we have no free will? That everything is predetermined? These are questions that go beyond physics, into philosophy, into the nature of consciousness itself. Physics can describe how the universe behaves, but it cannot tell us what it means, what we should make of it. That is for each person to decide, to feel, to understand in their own way. What I can tell you is that these ideas, these revelations about time and space, and what I can tell you is that these ideas, these revelations about time and space, they emerged not from complicated apparatus or vast laboratories, but from thought, from careful thought, from imagination, from questioning what seems obvious. The mind, the human mind, it is capable of grasping realities far beyond what our senses directly perceive. We cannot see space-time curving, we cannot feel time dilating in our daily lives, yet through reason, through mathematics, through careful observation, we can understand these things, we can know them to be true. This gives me hope, you see, hope that we can understand even deeper mysteries, even stranger aspects of reality that we have not yet imagined. The universe reveals itself slowly, reluctantly perhaps, but it does reveal itself to those who ask the right questions and listen carefully to the answers. Let us turn now to another aspect of these theories, something that puzzled many people when they first encountered it, the question of the ether, the luminiferous ether, as it was called. For centuries, physicists believed that waves must travel through some medium. Water waves travel through water, sound waves through air. So light waves, electromagnetic waves, surely they must travel through something. Yes? This hypothetical medium was called the ether, an invisible substance that filled all of space, penetrating everything, offering no resistance to motion, yet providing a substrate for light to propagate through. Many experiments were designed to detect this ether, to measure Earth's motion through it as our planet orbits the sun. The most famous was the Michelson-Morley experiment, an ingenious device using mirrors and light beams to detect even the tiniest difference in the speed of light in different directions. But they found nothing, no difference, no ether wind. Light traveled at the same speed in all directions, at all times of year, regardless of Earth's motion. This was deeply troubling. How could waves propagate without a medium? It seemed impossible, absurd even. The answer, as we have discussed, was that there is no ether. Light does not need a medium. It is a disturbance in the electromagnetic field itself, and fields are fundamental. They do not require any substrate. Empty space is not empty in the way we imagine emptiness. It is filled with fields, quantum fields, electromagnetic fields, gravitational fields, all the fundamental fields of nature. These fields are the reality, and particles, matter, light, they are excitations of these fields, waves in the fundamental ocean of existence. This was hard to accept, even for great scientists of the time. The human mind wants something solid, something tangible to hold on to. Empty space making waves in itself seems too abstract, too removed from experience. But nature does not care what we find easy to accept. Nature is what it is, and we must adjust our thinking to match reality, not the other way around. There is a lesson here, I think, about humility, about recognizing that our intuitions, developed over millions of years of evolution in a world of moderate speeds and moderate energies, these intuitions are not reliable guides to the fundamental nature of reality. We must be willing to abandon common sense when observation and logic lead us elsewhere. We must be willing to think thoughts that seem strange, to follow the mathematics wherever it leads, even when it takes us to places that feel uncomfortable or impossible. Now, I want to speak about something that connects these ideas to the very large, to cosmology, to the universe as a whole. You see, if space-time can curve, if mass and energy bend the fabric of space and time, then what about all the mass and energy in the universe? What does it do to space-time on the largest scales? This question, this natural extension of the ideas, leads to cosmology, to models of the entire universe. And what we find is remarkable. The universe is not static, not unchanging. It is dynamic, evolving, expanding. The space between galaxies is growing, stretching, carrying galaxies apart from each other like dots on an inflating balloon. This expansion was predicted by the equations of general relativity before it was observed. The mathematics suggested that the universe could not be static. It must be either expanding or contracting. At first, this seemed wrong. So wrong that well, let us say that even very smart people tried to modify the equations to allow for a static universe. A cosmological constant was introduced, a kind of energy inherent in space itself, pushing outward to balance the inward pull of gravity. But then observations by Edwin Hubble and others showed that distant galaxies are moving away from us, and the farther away they are, the faster they recede. The universe is expanding just as the unmodified equations predicted. Space itself is growing. Galaxies are not moving through space away from each other. Rather, the space between them is increasing. If the universe is expanding now, then in the past it was smaller, denser, hotter. If we trace this expansion backward in time, we arrive at a moment when everything, all the matter and energy in the observable universe, was compressed into an incredibly small, incredibly hot state. This is what we call the Big Bang, though that term is somewhat misleading. It was not an explosion in space, but an expansion of space itself, an expansion of space-time, carrying energy and matter with it. The Big Bang is not a theory about what caused the universe or why it exists. It is a description of what happened in the early universe, how it evolved from a hot, dense state to the cool, expanded state we see today. What happened before, or whether before even makes sense? These are questions that push the boundaries of what physics can currently address. But we have evidence, strong evidence, for this picture. The cosmic microwave background radiation, a faint glow of light that fills all of space, is leftover heat from the Big Bang itself. When the universe was very young, it was so hot that atoms could not form. Electrons and nuclei were torn apart by the intense energy. Light could not travel far before being scattered by these free electrons, so the universe was opaque, filled with a glowing plasma. But as the universe expanded, it cooled. Eventually, it became cool enough for electrons and nuclei to combine into atoms. Suddenly, light could travel freely. The universe became transparent. That light has been traveling through space ever since, stretched and cooled by the expansion, until now it appears as microwave radiation, corresponding to a temperature just a few degrees above absolute zero. This radiation was predicted by the theory before it was discovered. When it was finally detected accidentally by Arno Penzias and Robert Wilson using a radio antenna, it was immediately recognized as powerful confirmation of the Big Bang model. And the detailed pattern of tiny temperature variations in this radiation tells us about the structure of the universe when it was just a few 100,000 years old, about the seeds that would eventually grow into galaxies and clusters of galaxies. The expansion of the universe also explains the abundance of light elements like hydrogen and helium. In the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion to occur everywhere at once. Protons and neutrons combined to form deuterium, helium, tiny amounts of lithium. The predicted abundances of these elements match observations beautifully, another confirmation of the model. But there are mysteries, deep mysteries still. We observe that the expansion of the universe is accelerating, getting faster over time. This should not happen if only gravity is at work. Gravity should slow the expansion. Something else is acting, something we call dark energy, though we do not really know what it is. Perhaps it is the cosmological constant, that term that was added and then removed, and now seems to be necessary after all, representing some inherent energy of empty space itself. And there is dark matter, another mystery. When we observe galaxies and clusters of galaxies, they rotate and move in ways that suggest they contain far more mass than we can see in stars and gas. Something invisible, something that interacts gravitationally but does not emit light, seems to make up most of the matter in the universe. We call it dark matter, and despite decades of searching, we still do not know what it is made of. Perhaps undiscovered particles, perhaps something even stranger. These mysteries, they humble us. They remind us that for all we have learned, for all the success of these theories, we still understand only a small fraction of what the universe contains. Dark energy and dark matter together make up about 95% of the universe. Ordinary matter, the stuff we are made of, the stuff of stars and planets, it is only 5%, a tiny minority of cosmic constituents. Yet from this 5%, from ordinary matter obeying laws we understand, arose complexity, arose galaxies and stars, planets and chemistry, life and consciousness. The universe through us has become aware of itself, the universe through us has become aware of itself, has begun to contemplate its own existence, its own nature. This is extraordinary, is it not? That matter, organized in certain ways, can reflect upon matter, can discover the laws that govern its behavior. Consciousness arises from unconscious components. Understanding emerges from particles that do not themselves understand anything. How this happens, truly how this happens, remains one of the greatest mysteries. But let us return to the structure of these theories, to the way they fit together. Special relativity, as we have discussed, deals with objects moving at constant velocities, with the constancy of the speed of light and its consequences for time and space. General relativity extends these ideas to include acceleration and gravity, revealing gravity as geometry, as curvature of space-time itself. These theories are extraordinarily successful, tested to incredible precision in countless experiments and observations. Yet they are not complete, not final. They cannot be the last word, because they are inconsistent with another great pillar of modern physics, quantum mechanics. Quantum mechanics, this is a theory of the very small, of atoms and particles and the forces between them. It is strange in its own right, perhaps even stranger than relativity. It tells us that particles do not have definite positions or velocities until they are measured. That light can behave as both a wave and a particle. That events at the quantum level are fundamentally probabilistic, governed by chance in a way that seems irreducible. Now, general relativity is a classical theory, deterministic, continuous. Quantum mechanics is probabilistic, discrete, fundamentally different in character. Both are magnificently successful in their domains, but they do not fit together. When we try to apply the methods of quantum mechanics to gravity, to space-time itself, we encounter mathematical infinities, nonsensical results. The theory breaks down. This suggests that neither general relativity nor quantum mechanics is the final truth. They are approximations, extraordinarily good approximations within their respective domains, but approximations nonetheless. There must be a deeper theory, a quantum theory of gravity that unifies these two pillars and goes beyond them. Finding this theory, this is one of the great quests of modern physics. String theory, loop quantum gravity. Various approaches have been proposed, each with successes and challenges. We do not yet know which, if any, is correct. Perhaps the answer will surprise us completely, coming from a direction we have not yet imagined. But let me speak now about something more tangible, more directly testable, the phenomenon of gravitational lensing. We mentioned earlier that light bends when passing near massive objects. This means that massive objects can act like lenses, focusing and distorting light from more distant sources behind them. When we look at distant galaxies through telescopes, sometimes we see multiple images of the same galaxy, or images stretched into arcs and rings. This is gravitational lensing at work. A massive galaxy or cluster of galaxies between us and the distant source is bending the light, creating these distorted images. By studying these distortions carefully, we can map the distribution of mass in the lensing object, including the dark matter we cannot see directly. This has become a powerful tool for astronomy. We can weigh galaxies and clusters. We can detect dark matter. We can even use the time delays between multiple images of variable sources to measure the expansion rate of the universe. Nature has provided us with enormous lenses scattered throughout the cosmos, and we have learned to read what they tell us. There is also microlensing, where smaller objects like individual stars act as lenses. When one star passes in front of another from our perspective, the gravity of the foreground star briefly brightens the background star as it focuses the light toward us. This effect has been used to detect planets around other stars and to search for dark matter in the form of massive compact objects drifting through our galaxy. Every prediction, every strange consequence of these theories about curved spacetime and relative time has been confirmed when we found ways to test it. This gives us confidence that we are on the right track, that these mathematical abstractions correspond to something real about the universe. Now, let us consider time itself a bit more deeply. We have said that time is relative, that it runs at different rates for different observers. But what is time fundamentally? Is it something that exists independently, or is it merely a way of organizing our perceptions, a cognitive construct? In physics, time appears as a parameter in our equations, a coordinate labeling events just as spatial coordinates do. In general relativity, time is woven into space-time, losing some of its special character. We can even perform transformations that mix space and time coordinates, rotations in space-time that are analogous to ordinary rotations in space. Yet time feels different from space, does it not? We can move freely in space, forward or backward, left or right, up or down, but in time we seem to move only forward, never backward. Why? What distinguishes time from space in this way? This is related to what we call the arrow of time, the asymmetry between past and future. The fundamental laws of physics, both relativity and quantum mechanics, they are time symmetric. They work equally well forward or backward in time. If you watch a movie of planets orbiting a star or particles colliding, played backward, it would still obey the same laws. But the universe we experience is not time symmetric. We remember the past, not the future. Eggs break, but do not spontaneously reassemble. Heat flows from hot to cold, never the reverse without work being done. There is a directionality to time in the macroscopic world that is not present in the fundamental equations. The answer, we believe, lies in entropy, in the second law of thermodynamics. Entropy is a measure of disorder, of randomness, of the number of ways a system can be arranged while still appearing the same macroscopically. The second law states that entropy tends to increase that systems evolve toward more disordered states. A broken egg has higher entropy than an intact egg because there are many more ways to arrange broken shell fragments and scrambled molecules than to arrange them into a structured egg. The broken state is more probable, so systems tend to evolve toward it. This gives time its arrow, its directionality. But why was entropy low in the past? Why did the universe begin in a low entropy state at the Big Bang? This is a deep question, perhaps one of the deepest. If the early universe had started in a high entropy disordered state, there would be no arrow of time, no meaningful distinction between past and future. The fact that we exist, that there is structure and complexity, requires that the universe began in a very special, very ordered state. Why this should be so, we do not know. Perhaps it is explained by whatever physics governed the very earliest moments, the conditions that gave rise to the Big Bang itself. Perhaps there is a selection effect that only universes with low initial entropy can develop observers to wonder about such things. These are speculations, questions at the frontier of what we can sensibly discuss. But they are important questions because they touch on the nature of existence itself, on why there is something rather than nothing, why that something is structured and comprehensible rather than chaotic and meaningless. Physics can take us far, but perhaps not all the way to answers to such questions. Perhaps some questions lie beyond the reach of science, in the realm of philosophy or something else entirely. Time, consciousness, existence, these concepts interweave in ways we struggle to articulate. We experience time as flowing, as passing, yet physics describes a timeless block universe where all moments exist eternally. We experience consciousness as unified, as a single stream of awareness, yet we experience consciousness as unified, as a single stream of awareness, yet our brains are assemblies of billions of neurons, each following simple electrochemical rules with no awareness of their own. Where does the I emerge from this complexity? When does a collection of particles become an observer, a subject of experience? These questions, they lie at the intersection of physics, neuroscience, philosophy, perhaps touching upon territories we have not yet learned to map. There is something beautiful about uncertainty, about admitting what we do not know. Science progresses, not by claiming to have all answers, but by asking better questions, by refining our ignorance, if you will. Each answer opens new questions, deeper questions, questions we could not have even formulated before. Let me tell you about another curious consequence of relativity, something called length contraction. Just as moving clocks run slow, moving objects contract in the direction of their motion. A spaceship traveling at high speed would appear shorter to a stationary observer than it does to someone aboard the ship. This is not an optical illusion or a trick of measurement. It is a real physical effect, a consequence of how space and time relate to each other. From the perspective of someone on the spaceship, it is the outside universe that is contracted. A journey to a distant star might cover many light years, but at high enough speeds, length contraction makes the distance shorter from the traveler's perspective. Combined with time dilation, which gives the traveler less subjective time, interstellar travel becomes not easy, but at least theoretically possible within a human lifetime. Of course, accelerating to such speeds requires enormous energy. And there are other challenges, practical challenges like shielding against radiation and interstellar dust at such velocities. But the physics allows it. There is no fundamental barrier. The universe does not forbid us from exploring it. It merely makes the journey difficult. This raises interesting questions about the possibility of other civilizations, other intelligent beings in the universe. If interstellar travel is possible, even if difficult, and if life is common, then where is everyone? Why have we not encountered evidence of alien civilizations? This is the Fermi paradox, named after Enrico Fermi, who famously asked, "Where are they?" Perhaps life is much rarer than we imagine? Perhaps intelligence is rarer still? Perhaps civilizations destroy themselves before they can spread among the stars? Perhaps they are out there but hiding? Or perhaps they exist in forms we would not recognize, communicate in ways we cannot detect? Perhaps they visited Earth millions of years ago when there was nothing here to see but bacteria and algae. Perhaps they are here now, observing us, waiting to see what we will become. These are speculations, entertaining speculations, but speculations nonetheless. We simply do not know. We have one example of life, one example of intelligence, one example of technological civilization, and that example is ourselves. It is difficult to draw general conclusions from a sample size of one, but we are looking, we are searching. Projects like SETI, the search for extraterrestrial intelligence, scan the skies for artificial signals, for patterns that might indicate a technological civilization trying to communicate, or perhaps just going about their business in ways that leak detectable signals into space. So far, we have found nothing definitive, but the search has barely begun. The universe is vast, and we have examined only a tiny fraction of possible stars, possible frequencies, possible signaling methods. And now, with thousands of exoplanets discovered orbiting other stars, we know that planets are common. Many stars have planets, and many of those planets orbit in the habitable zone where liquid water could exist on the surface. The ingredients for life as we know it are widespread in the universe. Whether those ingredients actually assemble into living systems, whether those living systems develop intelligence, these remain open questions. But returning to our main theme, to the theories that changed our understanding of space and time, let us consider what happens at the extremes, in the most extreme environments the universe can produce. Black holes, as we mentioned, are regions where space-time curvature becomes so intense that not even light can escape. But what happens inside, beyond the event horizon? The mathematics tells us something remarkable and disturbing. Inside the event horizon, all paths lead to the center, to what we call the singularity. This is a point where curvature becomes infinite, where density becomes infinite, where our equations break down completely and can no longer make predictions. The singularity is not a place in space, but rather a moment in time, a moment that all infalling matter must reach. Or so the classical theory tells us, but we know that general relativity cannot be the whole story at such extremes. Quantum effects must become important when we reach such tiny scales, such enormous energies. The singularity is likely not real in the way the equations suggest, but rather a signal that we need a quantum theory of gravity to describe what actually happens there. Perhaps quantum gravity removes the singularity, replacing it with something else, some quantum structure we cannot yet imagine. Perhaps information that falls into a black hole is not lost, but encoded somehow on the event horizon, or preserved in ways we do not understand. These questions connect to deep problems in theoretical physics, questions about information conservation, and the relationship between quantum mechanics and gravity. Stephen Hawking showed that black holes are not entirely black. Through quantum effects near the event horizon, they emit radiation. They glow with thermal radiation as if they had a temperature. This Hawking radiation is incredibly faint for large black holes, but it means that black holes slowly evaporate, losing mass over time. Given enough time, unimaginable amounts of time, a black hole will completely evaporate, vanishing from the universe. This raises puzzles. If information falls into a black hole, and then the black hole evaporates, where does the information go? Quantum mechanics insists that information must be conserved, cannot be destroyed. But if it emerges in the Hawking radiation, how? The radiation appears thermal, random, carrying no information about what fell in. This is the black hole information paradox, a tension between general relativity and quantum mechanics that remains unresolved despite decades of work. Perhaps the resolution lies in recognizing that space and time themselves are emergent, not fundamental, that at the deepest level the universe is not made of space, time, and fields and particles, but of something more abstract, something like information or quantum entanglement from which space-time crystallizes under appropriate conditions. This is the direction much of modern theoretical physics is heading, toward understanding space-time as emergent rather than fundamental. These ideas are speculative, far from confirmed, but they represent attempts to resolve the deep conflicts between our two great theories, to find the quantum theory of gravity that will supersede both general relativity and quantum mechanics as we currently understand them. But even without resolving these deepest questions, the theories we have already developed, they work remarkably well. General relativity allows us to predict the orbits of satellites with centimeter precision, to synchronize GPS systems that must account for time dilation, both from motion and from the weaker gravity at satellite altitude. Without these corrections, GPS would drift out of alignment by kilometers in a single day. The atomic clocks on GPS satellites tick faster than clocks on the ground because they are further from Earth's gravitational field and experience weaker curvature of space-time. But they also tick slower because they are moving at high orbital speeds. Both effects must be accounted for, and they nearly but not quite cancel out. The net effect is about 38 microseconds per day, a tiny correction but absolutely crucial for accurate navigation. This is physics touching our daily lives, invisible corrections without which modern technology would fail. Every time someone uses GPS to navigate, they are relying on Einstein's theories of relativity. They are navigating through curved space-time with time flowing at different rates for satellites and ground receivers. Is that not remarkable? That such abstract, counterintuitive ideas have such practical applications? And the theories continue to surprise us with new predictions, new phenomena to discover. Gravitational waves were predicted in the early days of general relativity, but not detected for a century. Frame dragging, the effect where a rotating mass literally drags space-time around with it like honey stirred by a spoon. This was predicted but only confirmed recently by satellites carefully measuring the precession of orbits around Earth. The universe keeps confirming what the mathematics tells us, the universe keeps confirming what the mathematics tells us, keeps revealing that reality is stranger and more wonderful than we might have imagined. And this is what gives me such confidence in the power of human reason, in the ability of the mind to grasp truths that lie far beyond immediate sensory experience. Consider the equivalence principle, this beautiful insight at the heart of general relativity. It states that the effects of gravity are locally indistinguishable from acceleration. If you are in an elevator in a closed box with no windows, you cannot tell whether you are standing on Earth's surface feeling gravity pull you down, or whether the elevator is in deep space, accelerating upward at just the right rate to press you against the floor with the same force. The two situations are equivalent, physically identical. This seems simple, almost trivial perhaps, but it is profound. It means that gravity is not really a force in the traditional sense. When you stand on the ground, you do not feel gravity pulling you down. You feel the ground pushing you up, resisting your natural motion through curved space-time. If you were in free fall, falling freely toward Earth with nothing to stop you, you would feel weightless. You would be following the natural geodesic path through space-time, the straightest possible path given the curvature. Astronauts in orbit, they are falling, continuously falling around Earth, and they feel no gravity because they are following these natural paths. The International Space Station is not beyond Earth's gravity. The gravitational field there is only slightly weaker than at the surface. The weightlessness comes from free fall, from following the curved geometry of space-time without resistance. This is why we say that gravity is geometry. An orbit is not a balance between gravitational force and centrifugal force, though it can be described that way if you wish. More fundamentally, an orbit is simply a straight path through curved space-time, a four-dimensional helix in the fabric of space and time. Now, this geometric view of gravity has another beautiful consequence. If space-time can have different curvatures in different places, if it can curve around stars and planets, then perhaps space-time itself can have an overall shape, a global geometry. Perhaps the universe as a whole is curved in some way. There are three basic possibilities for the geometry of space, assuming it is uniform and the same in all directions, what we call homogeneous and isotropic. Space could be flat, like an infinite plane extending forever in all directions. Or it could have positive curvature, like the surface of a sphere, finite but without boundaries. Or it could have negative curvature, like a saddle shape, infinite and open. Which geometry describes our universe? This depends on the total density of matter and energy. If the density is exactly at a critical value, space is flat. If density is higher, space curves back on itself like a sphere. If lower, space curves outward like a saddle. Measurements of the cosmic microwave background, that ancient light from the early universe, these measurements tell us about the geometry of space. They look at the angular size of fluctuations in the temperature of this radiation, the pattern of hot and cold spots across the sky. This angular size depends on the geometry of space, just as the apparent size of distant objects depends on whether light travels through flat or curved space. And what we find, what the observations tell us, is that space is very close to flat, perhaps exactly flat within the measurement uncertainties. This is interesting because it means the density of the universe must be very close to the critical density, that special value that gives flat space. The ordinary matter we can see, and even the dark matter we infer from gravitational effects, they do not add up to enough. But when we include dark energy, that mysterious component causing the accelerated expansion, the total density comes out just right for flat space. Why should the universe be flat? Why should the density be so precisely at this critical value? This is another mystery, another puzzle suggesting that our understanding is incomplete. Some theories of the very early universe, theories of cosmic inflation, predict that space should be driven toward flatness by a brief period of extraordinarily rapid expansion in the first fraction of a second after the Big Bang. But these theories are speculative, not yet confirmed. Inflation is an interesting idea, though, worth discussing a bit. The standard Big Bang model, it works well, but has some puzzles. Why is the universe so uniform, so similar in all directions, when different regions were never in contact with each other, never had time to exchange light or information and equalize their properties? Why is space so close to flat when any deviation from flatness should grow over time, making flatness an unstable, improbable state? Inflation proposes that in the earliest moments, a tiny fraction of a second after the beginning, the universe underwent a period of exponential expansion, doubling in size again and again in rapid succession. A region smaller than an atom expanded to larger than the observable universe today in less time than it takes light to cross an atomic nucleus. This sounds absurd, impossible, but it solves the puzzles. A small region that was in thermal equilibrium, uniform and flat, gets stretched to enormous size. The observable universe today is just a tiny piece of this inflated region, which is why everything looks so uniform. We are seeing just a small patch that had time to equalize before inflation began. And the rapid expansion stretches space flat, ironing out any curvature like inflating a balloon, makes its surface appear flatter to an ant on the surface. Inflation also predicts the pattern of fluctuations we see in the cosmic microwave background. Quantum fluctuations in the inflating field got stretched to cosmic scales, frozen into the structure of space-time, becoming the seeds of galaxies and all cosmic structure. The detailed predictions match observations remarkably well, which is why many physicists take inflation seriously despite its speculative nature. But we do not know what caused inflation, what this inflaton field was, why it behaved the way it did. These are questions for future theories, future observations, future generations of physicists to address. Each answer we find opens new questions, deeper questions, questions that reveal yet more layers of reality to explore. There is something humbling and exhilarating about this, about recognizing how much we have learned and how much remains unknown. A century ago, we did not know about the expansion of the universe, about the Big Bang, about black holes or neutron stars or gravitational waves. We did not know about dark matter or dark energy. We thought we understood space and time completely, thought Newton had solved gravity once and for all. How much more will we discover in the next century? What phenomena that we cannot currently imagine will become as well established as time dilation and curved space-time are today? What technologies will emerge from deeper understanding as GPS emerged from relativity and transistors emerged from quantum mechanics? The universe is under no obligation to make sense to us, yet it does make sense. It follows laws, mathematical laws that we can discover and understand. Why should this be? Why should the universe be comprehensible to minds that evolved to hunt and gather on African savannas, minds that have no obvious need for understanding relativity or quantum mechanics or cosmology? Perhaps there is something deeper here, some connection between mind and cosmos that we glimpse only dimly. Perhaps consciousness is not merely an accident, an unlikely emergence from complexity, but somehow more fundamental, woven into the fabric of reality in ways we do not yet understand. These are philosophical speculations, I know, but physics leads us to the boundaries of such questions, even if it cannot answer them. Let me speak now about something more concrete, more tied to immediate observation, the precession of Mercury's orbit. This was one of the first great confirmations of general relativity, a problem that had puzzled astronomers for decades before the theory explained it perfectly. Mercury is the innermost planet, orbiting closest to the Sun, where space-time curvature is strongest among the planets. Its elliptical orbit is not fixed in space, but slowly rotates, precesses, with the point of closest approach to the Sun shifting gradually over time. Most of this precession can be explained by the gravitational influence of other planets, but there remains a tiny discrepancy, about 43 arc seconds per century, that Newtonian gravity cannot account for. General relativity predicts exactly this amount of extra precession as a consequence of the Sun's curvature of space-time. The prediction matched observation perfectly, one of the first signs that the theory was not just mathematically elegant, but physically correct. Such a small effect, less than 1/10,000th of a degree per year, yet it revealed the inadequacy of Newton's theory and pointed toward such a small effect, yet it revealed the inadequacy of Newton's theory and pointed toward a deeper understanding. This is how progress happens in science, you see, not through dramatic revolutions that overthrow everything, though it may seem that way, but through careful attention to small discrepancies, tiny anomalies that do not quite fit the prevailing theories. These little cracks in our understanding, they are where the light gets in, where new insights emerge. Newton's theory worked beautifully for centuries, predicted planetary motions with extraordinary accuracy, sent spacecraft to the moon and beyond. Yet it was not quite right. It was an approximation, excellent in most circumstances, but breaking down in the extreme case of Mercury's proximity to the Sun. General relativity includes Newton's theory as a special case, as what happens when gravity is weak and velocities are slow compared to light. In these everyday conditions, the two theories give nearly identical predictions. But general relativity is more accurate, more fundamental, valid even in the most extreme conditions we can observe. And yet, as we have discussed, even general relativity is not the final word. It too will eventually be superseded by a deeper theory that includes quantum effects, that unifies gravity with the other forces of nature. This is the way of science, always provisional, always open to revision when new evidence or better theories emerge. But each theory, each stage of understanding captures something true about reality, some aspect that remains valid even as we go deeper. Newton's laws are not wrong, they are incomplete. They work perfectly well for designing bridges and launching satellites. Similarly, general relativity will not be proven wrong when we finally understand quantum gravity. It will be recognized as a particular limit of a more comprehensive theory. Truth in physics is cumulative, layered, each level valid within its domain. Now, let me tell you about something that demonstrates the unity between energy, mass, and space-time curvature in a particularly striking way. When light, electromagnetic radiation, passes through space, it carries energy. And according to E equals mc squared, energy has mass equivalence. So light, even though it is massless in the traditional sense, even though individual photons have no rest mass, light itself should contribute to space-time curvature. Light should gravitate, and it does. In the early universe, when everything was much hotter and denser, radiation pressure, the pressure exerted by light and other massless particles, played a crucial role in the dynamics of the cosmos. Even today, in the intense environment near a black hole or inside massive stars, radiation pressure matters, contributes to the curvature, affects how matter behaves. There is even a theoretical possibility called a Kugelblitz, a black hole formed not from matter but from pure energy, from concentrated light. If you could focus enough electromagnetic energy into a small enough region, space-time would curve so strongly that it would form an event horizon, trapping the light itself. This is extraordinarily difficult, perhaps impossible with any technology we can imagine. But the theory allows it. Energy curves space-time, and sufficiently concentrated energy creates a black hole. This shows the deep connection between all forms of energy and the structure of space-time. Matter, radiation, even dark energy, all contribute to curvature, all participate in the gravitational dance. There is no fundamental distinction between these different forms of energy when it comes to gravity. The universe does not care whether energy comes from mass or motion or electromagnetic fields. It all curves space-time in accordance with the same equations. Speaking of electromagnetic fields, let us return for a moment to Maxwell's equations, those beautiful mathematical expressions describing electricity and magnetism. When Maxwell formulated these equations, he found something unexpected. They predicted the existence of electromagnetic waves traveling at a specific speed, a speed that turned out to match the measured speed of light. This led Maxwell to propose that light itself is an electromagnetic wave, a propagating oscillation of electric and magnetic fields. This unification of optics with electromagnetism was one of the great intellectual achievements of the 19th century. Phenomena that seemed completely different, light and electricity and magnetism, revealed as different aspects of a single underlying reality. The spectrum of electromagnetic radiation extends far beyond visible light, from radio waves with wavelengths of meters or kilometers through microwaves and infrared, visible light, ultraviolet, X-rays, all the way to gamma rays with wavelengths smaller than atomic nuclei. All the same phenomenon, all electromagnetic waves, differing only in frequency and wavelength. And all of it, all electromagnetic radiation, travels at the same speed in vacuum, that fundamental cosmic speed limit we have been discussing. This is not a coincidence, but a deep consequence of the structure of space-time itself. The speed of light is really the speed of causality, the maximum rate at which information can propagate, the speed at which cause and effect can connect distant events. Anything without mass, anything that does not experience time in its own reference frame, must travel at this speed. Photons experience no time at all, if we could speak of their perspective, which we cannot quite do. From a photon's point of view, if such a thing made sense, emission and absorption happen simultaneously. The journey across the universe takes no time. This is hard to wrap one's mind around, but it follows from taking time dilation to its logical extreme. As speed approaches the speed of light, time dilation approaches infinity, time stops. This is why nothing with mass can reach the speed of light. It would require infinite energy to accelerate to that speed, and time would stop for the object. The speed of light is not just a barrier you run into, it is more like an asymptote, something you can approach ever more closely but never quite reach, no matter how much energy you expend. Yet light itself, massless light, travels at exactly this speed effortlessly, naturally, because it is the speed that the geometry of space-time permits for massless entities. There is something deeply satisfying about this, about how all the pieces fit together, how the constancy of light speed, time dilation, length contraction, mass energy equivalence, space-time curvature, all emerge from the same fundamental structure, all connect and support each other in a coherent whole. Let me turn now to a more speculative topic, something at the edge of current understanding. Wormholes. These are theoretical structures, solutions to the equations of general relativity that connect distant points in space-time through a kind of tunnel or shortcut. If they exist, and this is a big if, they might allow travel between distant locations faster than light could traverse the intervening space without actually exceeding the speed of light locally. The idea is this: space-time could be curved in such a way that two regions far apart in ordinary space are connected by a bridge, a throat through a higher dimension that creates a much shorter path. You enter one mouth of the wormhole here, travel through the throat, and emerge from the other mouth, light years away, having traversed the distance in less time than light would take, traveling the normal route through space. This sounds like science fiction, and indeed it is a staple of science fiction stories. But the mathematics of general relativity allows such structures. They are valid solutions to the equations. The question is whether nature actually produces them, and if so, whether they could be traversable, whether anything could actually pass through. The problem is that the known solutions for traversable wormholes require what we call exotic matter, matter with negative energy density. This is not ordinary matter. It is something that would violate what we call energy conditions, requirements that seem necessary for reality to behave sensibly. We have never observed exotic matter, never seen anything with negative energy density on macroscopic scales. There are quantum effects that can produce negative energy locally for brief moments, what we call the Casimir effect or Hawking radiation near black holes. But whether enough exotic matter could be assembled and stabilized to hold open a wormhole, this is deeply uncertain. Most physicists suspect that traversable wormholes do not exist, that quantum gravity effects we do not yet understand will forbid them, will close the loopholes in general relativity that seem to permit such structures. But we do not know for certain. Until we have a complete theory of quantum gravity, we cannot say definitively what is possible and what is not. Perhaps wormholes are possible, perhaps they occur naturally in the universe, or could be created by sufficiently advanced technology. Perhaps the universe is not quite as constrained as we think. Perhaps there are shortcuts, backdoors, ways around the limitations that appear fundamental. This is the joy and the frustration of being at the frontier of knowledge. So much is uncertain, so many questions remain open. We know so much more than our predecessors, yet we also know how much we do not know. The known universe has expanded dramatically, but so has the boundary between the known and the unknown, and it is at that boundary where the most interesting questions live. Let us consider another implication of relativity, something called the relativity of energy. Just as time and space and simultaneity are relative, depending on the observer's state of motion, so too is energy. The energy of a particle or object depends on the reference frame from which you measure it. Something at rest has only its rest mass energy, E equals mc squared, but if it is moving relative to you, it has additional kinetic energy, energy of motion. And here's the interesting part. As velocity increases, approaching the speed of light, the kinetic energy grows without bound. It takes more and more energy to produce smaller and smaller increases in velocity. This is why we cannot accelerate massive objects to the speed of light. The energy required becomes infinite as we approach that limit. In particle accelerators, we see this directly. Electrons or protons accelerated to nearly the speed of light become extraordinarily energetic, carrying millions or billions of times their rest mass energy as kinetic energy. Yet they never quite reach that ultimate speed. They asymptotically approach it, getting closer and closer, but never arriving. We can accelerate particles to 99.9999% of the speed of light and beyond, adding more and more nines but never reaching 100%. The energy cost becomes prohibitive long before we get there, each additional increment requiring exponentially more energy than the last. This is not a limitation of our technology, but a feature of reality itself. The universe imposes this speed limit not through some barrier or resistance, but through the very structure of space and time. It is woven into the fabric of existence, unavoidable, absolute in its relativity, if you will permit the paradox. But let me speak about something that brings these abstract ideas closer to human experience. Time dilation affects not just particles in accelerators or clocks on satellites, but potentially human lives. The twin paradox, as it is called, though it is not really a paradox, illustrates this beautifully. Imagine two twins, one stays on Earth, the other travels on a spacecraft to a distant star and returns. The traveling twin experiences less time than the stay-at-home twin, returning younger than their sibling. This is not symmetrical, even though we have said motion is relative. The traveling twin accelerates, turns around, experiences forces, and changes in velocity. They change reference frames, while the earthbound twin remains essentially in one frame throughout. The resolution comes from understanding that acceleration is absolute, in a sense that velocity is not. You can feel acceleration. It presses you into your seat or makes you weightless. You cannot feel constant velocity. There is no experiment you can do inside a sealed spacecraft moving at constant speed that tells you you are moving, but acceleration that you can detect that makes the situations non-symmetrical. When we carefully work through the mathematics, accounting for the different reference frames during different parts of the journey, we find that both twins agree on the outcome. The traveler has aged less, has experienced less time. This is not a matter of perspective or interpretation. It is a physical reality that both observers can verify and agree upon. For velocities achievable with current or foreseeable technology, the effect is small, but it is real and measurable. Astronauts who spend months on the International Space Station orbiting at high speed in a weaker gravitational field, they return having aged slightly less than they would have on Earth. The effect is tiny, milliseconds over months, but it accumulates. It is there. If we could somehow accelerate a spacecraft to a substantial fraction of light speed, if we could maintain such speeds for long journeys, time dilation would become dramatic. A journey to the center of our galaxy, tens of thousands of light years away, might take only decades of subjective time for the travelers if they could somehow travel fast enough. They would arrive to find that tens of thousands of years had passed on Earth, everyone they knew long dead, civilization transformed beyond recognition. They would be time travelers into the future, unable to return to their own era. This is theoretically possible, but practically beyond our current capabilities by an enormous margin. The energy required to accelerate even a small spacecraft to such speeds is staggering, far beyond anything we can harness. And the dangers of traveling at such velocities, collisions with even tiny particles releasing catastrophic amounts of energy, these are formidable obstacles. Yet there is no law of physics that forbids it. The universe permits such journeys, even if they are extraordinarily difficult. Perhaps one day, perhaps centuries or millennia from now, humans or their descendants will undertake such voyages. Perhaps they already have, somewhere else in the universe, other civilizations exploring the cosmos, navigating through curved space-time, experiencing time dilation as they travel between stars. Now, let me speak about another prediction of general relativity that has profound implications. The existence of gravitational time dilation, even in static gravitational fields. It is not just motion that affects time, but gravity itself, or rather the curvature of space-time associated with gravity. A clock at the bottom of a gravitational well, closer to a massive object, runs slower than a clock higher up, where gravity is weaker and space-time less curved. This effect is small on Earth, but measurable. Atomic clocks at different altitudes tick at measurably different rates. A clock on the ground floor of a building runs slower than one on the top floor by a tiny but detectable amount. The Global Positioning System, GPS, must account for this. Satellites orbit high above Earth where gravity is weaker, where space-time is less curved, and their clocks run faster than clocks on the surface. Without correcting for this effect, GPS positions would drift by kilometers in a matter of hours, rendering the system useless for navigation. So every time you use your phone to find directions, you are benefiting from corrections based on general relativity. The satellites are constantly adjusting their clocks, compensating for the fact that they experience time differently than you do on the surface. This is relativity in action, not abstract theory, but practical technology touching daily life. Near more extreme gravitational fields, near neutron stars or black holes, time dilation becomes dramatic. A clock on the surface of a neutron star, where gravity is millions of times stronger than on Earth, would run noticeably slower than a clock far away. Near the event horizon of a black hole, time dilation becomes infinite. Time effectively stops at the horizon from the perspective of a distant observer. This creates a strange situation. If you watch someone fall into a black hole, you never actually see them cross the event horizon. They appear to slow down, to freeze as they approach the horizon, their image becoming redder and dimmer, fading away but never quite crossing that boundary. But from the infalling person's perspective, they cross the horizon in finite time. They experience nothing special at that moment. They simply pass the point of no return and continue falling toward the singularity at the center. This difference in perspectives, this radical disagreement about what happens, is one of the puzzles that makes black holes so fascinating and so challenging to understand fully. Different observers have fundamentally different experiences, different descriptions of events, yet both are valid within their own reference frames. Reconciling these perspectives requires careful thought about what we mean by events and simultaneity in observation. Black holes also raise questions about the ultimate fate of matter and information. If something falls into a black hole, crossing the event horizon, can we ever retrieve information about it? Classical general relativity says no. The information is lost behind the horizon, eventually consumed by the singularity. But quantum mechanics insists that information cannot be destroyed. It must be preserved in some form. This tension, this apparent contradiction between general relativity and quantum mechanics in the context of black holes, has driven much research in theoretical physics for decades. Hawking radiation, which we mentioned earlier, provides one possible resolution. Perhaps information does escape, encoded subtly in the radiation emitted by the black hole, though exactly how this encoding works remains controversial and unclear. Some proposals suggest that information is stored on the event horizon itself, smeared across its surface in a kind of holographic encoding. The idea is that a three-dimensional volume of space can be fully described by information encoded on its two-dimensional boundary, like a hologram that appears three-dimensional but is really a flat surface. If this holographic principle is correct, then the information about everything that falls into a black hole might be preserved on the horizon, available to be released as the black hole evaporates. These ideas push the boundaries of current understanding, combining concepts from quantum mechanics, information theory, thermodynamics, and general relativity in ways that reveal deep connections between these different areas of physics. The study of black holes has become a laboratory for exploring quantum gravity, for testing ideas about how these theories might be unified. And what we learn from thinking about black holes may have implications far beyond black holes themselves. The holographic principle, if true, might apply to the universe as a whole. Perhaps all of reality, everything we experience as three-dimensional space, is actually encoded on some distant boundary, some surface at the edge of the cosmos. We would be living inside a kind of hologram, though this does not mean our experiences are any less real, just that the fundamental description of reality might be simpler, might live on a lower dimensional surface. This sounds like wild speculation, I know, like something from philosophy or mysticism rather than physics. But these ideas emerge from taking seriously the mathematics of general relativity and quantum mechanics, from following where the equations lead. They may be wrong, our current mathematics may be misleading us, but they illustrate how deeply strange reality may be at its foundations, how far from common sense the truth might turn out to be. Yet all of this strangeness, all these counterintuitive predictions, they rest on a foundation of observation and experiment. We believe in time dilation because we measure it. We believe in curved space-time because we observe gravitational lensing and the precession of Mercury's orbit. We believe in black holes because we detect gravitational waves from colliding black holes and see images of their shadows. We believe in the Big Bang because we observe the cosmic microwave background and the expansion of the universe. Theory guides us, mathematics points the way, but ultimately, it is nature that decides. It is observation, measurement, careful experimentation that determines which ideas survive and which must be discarded or modified. Physics is not purely abstract thought. It is a conversation with reality, a dialogue where we propose ideas and nature responds, sometimes confirming our hypotheses, sometimes surprising us with unexpected answers. And nature is patient, infinitely patient. It does not care whether we understand it or not, whether our theories are elegant or clumsy. It simply is what it is, following its own rules with perfect consistency. Our job, our privilege really, is to discover those rules, to decode the patterns, to find the underlying order that makes the universe comprehensible. Let me tell you about something that illustrates this interplay between theory and observation beautifully: the discovery of Neptune. In the mid-19th century, astronomers noticed that Uranus, the seventh planet, was not following the orbit predicted by Newton's law of gravity. There were small but persistent deviations, tiny anomalies in its motion. Two possibilities existed. Either Newton's law was wrong, needed modification, or there was another planet, an undiscovered eighth planet, whose gravitational influence was perturbing Uranus's orbit. Several mathematicians calculated where this hypothetical planet should be, working backward from the observed perturbations to predict its location. and when astronomers pointed their telescopes to the predicted position, there it was. Neptune, right where the calculations said it should be. This was a magnificent triumph for Newtonian physics, confirmation that the theory was powerful enough to predict the existence of unknown worlds. Yet decades later, a similar anomaly in Mercury's orbit could not be explained by an undiscovered planet. That anomaly required general relativity, required abandoning Newton's theory for a deeper understanding of gravity. Both situations involved unexplained motion, but they had different resolutions. This shows the importance of testing, of not assuming our theories are correct, of remaining open to the possibility that even successful theories might need modification or replacement. Neptune vindicated Newton, Mercury vindicated Einstein. Both discoveries advanced our understanding. Both taught us something essential about how science progresses. Now, I want to touch on something more philosophical, more reflective. The arrow of time, which we discussed earlier, it raises questions about free will, about determinism, about the nature of choice. If the laws of physics are time symmetric, if they work equally well forward and backward in time, then is the future already determined? Is it already out there in space-time waiting for us to experience it? Some interpretations of relativity suggest this. The block universe view, as it is called, sees space-time as a four-dimensional whole where all moments of time exist equally, where past and future are as real as the present. We experience time as flowing, moving from past through present to future, but this flow might be an illusion of consciousness, a feature of how we process information rather than a fundamental aspect of reality. If this is true, if the future already exists in some timeless sense, does that mean our choices are not real? That we have no freedom, no agency? These are deep questions, questions that physics alone cannot answer. The equations describe what happens. They predict correlations between events, but they do not tell us what it feels like to be a conscious agent making choices. Perhaps determinism and free will are compatible. Perhaps they operate at different levels of description. Perhaps the microscopic level is deterministic, following precise laws, while the macroscopic level, the level of conscious experience, exhibits genuine freedom through mechanisms we do not yet understand. Perhaps consciousness itself plays a role in collapsing quantum superpositions, in selecting which potential futures become actual, though this is highly speculative. Or perhaps the block universe view is wrong. Perhaps time really does flow. Perhaps there is something special about the present moment that our equations fail to capture. We do not know. These questions sit at the boundary between physics, philosophy, and perhaps neuroscience, awaiting insights that may come from unexpected directions. What I can say is that regardless of whether free will exists in some ultimate metaphysical sense, we experience choice, we experience agency. We must act as if our decisions matter. And perhaps that is enough. Perhaps the subjective experience of freedom is what matters, regardless of the underlying reality. Let me return to more concrete matters. The speed of light, we have said, is constant, the same for all observers. But what determines this speed? Why is it approximately 300,000 kilometers per second and not some other value? Is this an arbitrary fact about our universe, or is it related to something deeper? In natural units, the units that physicists often use when doing theoretical work, the speed of light is simply one. It is the fundamental unit of velocity, and all other speeds are fractions of this speed. Time and space are measured in the same units, converted by multiplying or dividing by the speed of light. In this system, the speed of light is not a specific number, but a fundamental ratio that relates space and time. The actual numerical value we measure, 300,000 kilometers per second, depends on our arbitrary choices of units, kilometers and seconds, units developed for practical purposes long before we understood relativity. If we use different units, We would get a different number, but the physics would be identical. The speed of light is fundamental, but its numerical value in any particular unit system is not. What is fundamental is that there exists a maximum speed, a cosmic speed limit, and that this speed is the same for all observers. This speed is built into the structure of space-time itself. It is a conversion factor between space and time, telling us how much time corresponds to how much space in the geometry of the universe. Other fundamental constants also appear arbitrary at first glance. Planck's constant, which sets the scale of quantum effects, the gravitational constant, which determines the strength of gravity, the fine structure constant, which characterizes the strength of electromagnetic interactions. These numbers seem random, specific values without obvious justification, but perhaps they are not arbitrary. Perhaps in a complete theory, a true theory of everything, these constants would be calculable, would emerge as necessary consequences of the mathematical structure. Or perhaps there are many universes, each with different values of these constants, and we find ourselves in one where the values permit stars and planets and life to exist. Most other combinations might produce universes that are sterile, lifeless, where no observers could arise to wonder about such things. This anthropic reasoning is controversial. Some physicists find it unsatisfying, too close to giving up on finding deeper explanations. But it may be the truth. The universe may be fundamentally probabilistic at some level, with our particular constants selected from a vast landscape of possibilities by the requirement that observers must exist to measure them. We do not know. Like so many questions at the frontiers of physics, we have ideas, proposals, hints, but not definitive answers. And that is fine. That is how science works. We push forward with incomplete knowledge. We explore different possibilities. We remain open to being surprised. Let me speak about one more aspect of general relativity, something I find particularly beautiful. The idea that the laws of physics should be the same for all observers, regardless of their motion or their position in a gravitational field. This is the principle of general covariance, the idea that the form of physical laws should not depend on the coordinate system you choose to describe events. This might sound abstract or technical, but it has profound implications. It means that physics is coordinate independent, that the underlying reality does not care how we choose to label events, what coordinate system we adopt. Different observers might use different coordinates, different ways of measuring space and time, but they will all agree on physical predictions on what actually happens. This is a kind of democracy of perspectives. No observer is privileged, no reference frame is special. The laws of physics are universal, applying everywhere and everywhen in the same form. This universality is one of the great insights of modern physics, a recognition that reality transcends our particular perspective, that truth is objective even when measurements are relative. And this brings us to something profound about the scientific enterprise itself. We seek universal truths, patterns that hold everywhere, laws that do not depend on who discovers them or when or where. Science is a collective human endeavor, but its fruits, its discoveries, they belong to everyone. They describe a reality that exists independently of, and this brings us to something profound about the scientific enterprise itself. We seek universal truths, patterns that hold everywhere, laws that do not depend on who discovers them or when or where. Science is a collective human endeavor, but its fruits, its discoveries, they belong to everyone. They describe a reality that exists independently of human culture or preference or belief. A theorem proven in ancient Greece remains true today. The orbit of a planet calculated by astronomers in different countries, speaking different languages, yields the same result. The speed of light measured in laboratories across the world gives the same value. This universality, this consistency, It tells us that we are discovering something real, something that transcends individual minds or cultural contexts. And yet, the process of discovery is deeply human, deeply personal. The questions we ask, the problems we choose to investigate, the way we interpret results, all of this bears the stamp of human consciousness, human curiosity, human values. We study the universe not as disembodied intelligences, but as embodied beings with emotions, with aesthetic sensibilities, with desires to understand our place in the cosmos. The theories we have discussed, these insights about time and space and gravity, they emerged from human minds grappling with puzzles, following intuitions, making imaginative leaps. The mathematics may be abstract, but the motivation is human. We want to know. We want to understand. This desire, this drive to comprehend, it seems to be fundamental to consciousness itself, at least to human consciousness. Perhaps this drive is what will carry us forward, what will enable future generations to solve the mysteries that remain. The nature of dark matter and dark energy, the unification of quantum mechanics and gravity, the origin of the universe, if that question even makes sense, the possibility of other universes beyond our own, the emergence of consciousness from unconscious matter, the ultimate fate of everything. These are grand questions, perhaps the grandest questions we can ask. And we may not answer all of them, we may never answer some of them. But the pursuit itself, the journey of exploration and discovery, this gives meaning to the human enterprise. It connects us to something larger than ourselves, to the cosmos that gave birth to us, to the billions of years of cosmic evolution that led from the Big Bang to galaxies and stars, planets and chemistry, life and mind. We are, in a very real sense, the universe becoming aware of itself. We are stardust contemplating stars, atoms pondering atoms, consciousness emerging from the quantum foam to question its own existence. This is extraordinary, miraculous, even if we use that word in a naturalistic sense, meaning deeply improbable and precious rather than supernatural. The elements in your body, the carbon and oxygen and nitrogen, they were forged in the cores of ancient stars that exploded billions of years ago, scattering their enriched material into space, where it eventually collected into new stars, new planets, new possibilities. You are made of star stuff, as Carl Sagan so memorably said, and not just made of it, but arranged in such intricate patterns that you can understand this fact, can trace your atomic ancestry back to stellar furnaces that died before Earth existed. General relativity and special relativity, these theories we have explored together, they are part of this story. They describe the stage on which the cosmic drama unfolds, the space-time arena where matter and energy dance, where causality propagates, where existence happens. Without understanding relativity, we cannot fully grasp how the universe works, how gravity shapes the cosmos, how time and space interweave to create the fabric of reality. And this understanding, hard won through decades of thought and observation and calculation, it changes us. It expands our minds, our sense of what is possible, our appreciation for the strange and wonderful universe we inhabit. We can never return to the innocent certainty that space and time are absolute, that simultaneity is universal, that gravity is a force acting at a distance. We have seen deeper, glimpsed the geometric structure underlying these phenomena, and we are forever changed by that glimpse. This is the gift that science offers, not just technological applications, though those are valuable, but a transformed understanding, a new way of seeing. The universe becomes more marvelous the more we learn about it, not less. The poetry of reality, if I may call it that, exceeds anything we could have imagined before we looked carefully at what nature is actually doing. And there is so much more to discover, so many layers still hidden, so many questions unanswered. We stand at a moment in human history where we understand enough to know how much we do not understand. The known territory has expanded tremendously in the past century, but the boundary with the unknown has expanded even more. Every answer generates new questions. Every solution reveals new puzzles. This is not frustrating, or it need not be. It is exhilarating. It means the adventure continues. The story is far from over. Future generations will look back at our time as we look back at the early 20th century, marveling at what we did not know, perhaps amused by our misconceptions, but hopefully appreciating the progress we made, the foundations we laid for their deeper understanding. The theories of relativity will remain, I believe, as permanent achievements of human thought, as fundamental insights that future theories will build upon rather than overturn. Just as thermodynamics survived the quantum revolution, just as Newton's laws remain valid in their appropriate domain, relativity will endure as a description of how space-time behaves, how gravity works, how motion affects the passage of time. But we will go deeper. We will understand the quantum nature of space-time, the origin of these classical equations, from some more fundamental quantum substrate. We will perhaps understand why the universe has the properties it does, why these laws rather than others. We will perhaps discover that our universe is one of many, part of a larger multiverse, or perhaps we will find that it is unique, the only possible universe given some deep mathematical necessity we have not yet glimpsed. I do not know what we will discover. I only know that we will discover. Humanity will continue to explore, to question, to seek understanding. This is our nature, what distinguishes us, what makes us human. We are the beings who ask why, who look at the stars and wonder, who build instruments and theories to extend our senses and our reasoning beyond their natural limits. And in this exploration we find meaning, not a meaning handed down from above, not a purpose imposed from outside, but meaning we create through understanding, through connection, through participation in the grand project of making sense of existence. We matter because we ask questions. We matter because we seek truth. We matter because we are conscious witnesses to the universe, nodes of awareness in the vast web of causality. So rest now. Let these ideas settle in your mind. Let the strangeness of time dilation, the elegance of curved space-time, the unity of mass and energy, let these concepts find their place in your understanding. You do not need to grasp every detail, every equation. What matters is the broad vision, the sense that reality is deeper and stranger and more beautiful than common sense suggests. Sleep with the knowledge that you live in a universe of extraordinary richness, where space and time curve and flow, where gravity is geometry, where the past and future connect through the eternal present of space-time. You are part of this universe, made of its substance, subject to its laws, yet capable of understanding those laws, of grasping truths that transcend your immediate experience. This is the legacy of these theories, these revolutions in thought that changed physics forever. They changed not just our equations and predictions, but our conception of reality itself, our place in the cosmos, our understanding of what is possible and what is necessary. And if you found value in this exploration, if these ideas sparked wonder or curiosity or deeper questions in your mind, I would be grateful if you would subscribe to this channel, if you would like this video, if you would share it with others who might appreciate falling asleep to high-quality knowledge. Help us build a community of curious minds, of people who want to learn even as they rest, who recognize that education and relaxation need not be separate, that the best way to end a day might be with wonder rather than worry. Thank you for spending these hours with me, exploring the deepest insights about space and time that human minds have yet achieved. May you sleep well. May you dream of curved space-time and time-traveling twins, of black holes and cosmic expansion, of the elegant mathematics that describes it all. The universe awaits your further exploration. But for now, rest. Let go. Allow sleep to come naturally as it will. You have earned it by engaging with these challenging ideas. by stretching your mind to encompass the strange truths that relativity reveals. Good night, sleep well, and may you wake tomorrow with renewed curiosity about this remarkable universe we are privileged to inhabit and explore.